we have a set of optical transmitters from 1 to n, which are able to provide at the exit a modulated light with the appropriate lambda. If you are able to read, we have the first transmitter, which is lambda 1, the second is lambda 2, until the last one, which is lambda n. This kind of transmitter is normally called colored transmitter, because when you order it, you say, I'd like to buy a transmitter working on the wavelength C40, dove C, where C is the name of the bandwidth you are using. C stands for conventional, as we shall see later, and 40 is the number of the channel inside that bandwidth. All the transmitters are connected to an optical multiplexer, which collect all the lambdas and output them all together on the same output fiber, in a way that I call comb, but it's a collection of lambdas. As we did for television, also for optical communication, the wavelengths are assigned. You cannot choose the wavelength you like, but you have to stay on a grid which is provided by a ITU recommendation. After the output from the transmitting equipment, we have the link, which is normally made up by fiber section plus optical amplifier. I will not insist on optical amplifier since you have been already exposed to the theory of optical amplifiers. What I want to stress is that optical amplifier is an analog device. Analog device simply means that I send inside the optical amplifier a signal, I collect at the exit the same signal, amplified, for example, by 25 dB, which is a lot, but with added noise. Because the amplifier itself, even if it's not fed by any signal, will emit light. It is substantially, it is a laser, a fiber laser, the optical amplifier. If don't send any signal inside it, the laser will emit light, and this light is noise because it is added to your signal. Unfortunately, this noise is emitted in the same bandwidth of the signal, so that we cannot separate it. There is a part which is out of the bandwidth and we can filter, but a lot of noise, which is called amplified spontaneous emission, is in the signal bandwidth. What does it mean from a design point of view? It simply means that you have to limit the number of amplifiers along the lines. You cannot go from here to New York simply putting an amplifier every 50 kilometers or 60 or 70 kilometers, because the signal, the noise which is added to the signal will destroy the signal. And the noise is very much. The amplifier add a lot of noise so that the maximum number of amplifier that can be cascaded can be counted on the finger of a hand, 5 or 6 as a maximum. But since the amplifier is inserted every 80 kilometers, you simply understand that you can go from a transmitter to a complete receiver for 500 kilometers without having no electric system along the line, only amplifiers. They are a few, 5, but are spaced 80 kilometers apart, so that it is 500 kilometers from the transmitting end to the receiving end. When we reach the receiving end, the signal is demultiplexed. The demultiplex is exactly the same than the multiplex, except the fact it is fed by the other port, and all the original lambdas are recovered and detected by the receivers. The receivers are wideband receivers, so they are all equal. You can put the receiver there, any receiver, you can exchange them. They are wide bandwidth, are able to detect any lambda. By the way, one thing that is seldom said concerning optical multiplexers, the optical multiplexer is a completely reversible system, which means that if I turn it 180 degrees, it will work. And this is the confirmation. But it can also work, and it will be very important tomorrow for access networks, in a mixed way. Think of the optical multiplexer as a Newton prism. It is just like a Newton prism. You enter with white light and you exit with the colors of the arrows. It works this way, but it is also reversible. It's difficult to operate it, but it works. If you enter with the colors of the arrow with the exact inclination, you will get white light. But you can do something more. You can have white light entering from one side and some of the lambdas entering from the other side. They will go through the exit. It will not white light because you are not sending all the colors that are needed to form a white light. But you can use in the other way around. What does it mean here? It means that if from the signal here I remove, for example, lambda 2, all the lambda except lambda 2 will go to the receiver. In this direction, I can send lambda 2 and it will go to the fiber. This is a very important point which is normally not told during explication of working of a multiplexer and the multiplexer. We shall see an application tomorrow. What is the application of a point-to-point link? Well, it is the simplest of the optical transmission system. It is able to transport information between 2 points, and it is able to transmit information starting from a few kilometers up to thousands of kilometers. a few kilometers is put there only for convenience. In the reality, you can have a transmitter and a receiver which are a few meters apart. They are not of interest to ITU, so normally we speak of a few kilometers, which actually means 600 meters for equipment interconnection in the central office. So we start from connection inside the building or between two very close buildings, and we end to transmission across continents. When we have a transatlantic or transpacific cable, we go from one terminal equipment to the other terminal equipment under the water for several thousand of kilometers. This is what I was insisting before. From a principal point of view, I could go everywhere with a point-to-point link. When the attenuation increases to, let's say, 25 dBs, I put an amplifier for 25 dBs, and I have back the original signal. This is not true, because as we said, the original signal is degraded by the addition of noise and by fiber impairments. You learned that fibers has chromatic dispersion, which means that light of different colors travel at different velocity, which means that the various lambda are delayed. They use different times to travel along the fibers, but this is not the problem. The problem is that inside the single wavelength, the pulse is large and the different colors of the pulse are delayed each to the other, which means at the end that the pulse is broadened, which is not good from a point of view of digital transmission. So we have to compensate for such a dispersion. Moreover, when a lot of lambdas travels along the fibers and are simultaneously amplified, they incur in some nonlinear effects, which means mainly self-phase modulation, the pulse modify its shape, or cross-phase modulation, one pulse modifies the shape of an adjacent pulse, or four-way mixing. Four-way mixing is intermodulation. So if we have two lambda that are beatings between them, a third lambda will be created. If the third lambda is coinciding with another signal, it will interfere. This is the most important effects from the nonlinear point of view. The meaning of what I have just said, that with the optical amplifiers and WDM, we are back in an analog world. We started analog. We turned to all digital. Now we are back in the analog world. Rule of thumb is not, of course, the answer could be very simple. It depends on the system. but I will be more precise, and I will say you two things. The first one is that the normal distance between amplifiers is as high as 80 kilometers. The second thing I will say you is that the number of amplifier is 6 as a maximum. Maybe if you make some joint engineering, you can have a 7 or 8, but you can go 500 kilometers. But I want to add another thing. We have plenty of tables afterwards in which the characteristics of the system are detailed. What I want to stress is that we saw at the beginning a long list of recommendations. The scope of this tutorial is to tell you that the recommendation exists and they are dealing with different systems. Since the systems are 50 or 60 different systems, I cannot tell you this system is able to go to 48 kilometers with such an attenuation. All the data are in the recommendation. I collected some of them in tables, the most important of them in tables, but I am a human being. I cannot have all the numbers for 50 or 60 different systems. As an engineer, not an ITU man, as an engineer, what I learned is that maximum distance is 80 kilometers and the number of amplifier you can cascade is 5, 6, 7. Of course, it depends on many things. It will change when we are going to use 100 gigabit per second, because 80 is good for 10 gigabit per second or eventually 40 gigabit per second. It will not good for 100 gigabit per second, or it can be good and the distance could be increased to 100 kilometers between amplifier if we discovered some other means to transmit information. Because if we should have a course on optical fiber system, it should last like a university course, 6 months. But there are aspects which are not dealt with here. For example, the improvement we had in the modulation. At the beginning, we simply had the laser switched on and off, which actually means switched between high level and low level. I am not going to switch off the laser. Otherwise, it will take 3 nanoseconds to switch it on, and I am not able to transmit high bit rates in this way. But this was only the beginning. It is like the crystal radio of the 20s or the 30s. It's a very bad way to use optical transmission. Now we have a very sophisticated transmission modulation, which means return to zero, or coherent transmission, which means phase modulation, differential phase modulation, frequency modulation, ASK, and all this kind of transmission are able to correct some impairments. For example, think about the simplest. The distinction between no return to zero and return to zero. In no return to zero, I have 1, 1, 1, 0, 1, and so on. In return to zero, I have 1, 0, 1. So the pulse is only half of the bit time. Well, it is clear that, first, the impact of chromatic dispersion will be lower because I start from a very narrow pulse. The chromatic dispersion will try to enlarge it, but I start from half the size. On the other hand, I will need double bandwidth because return to zero has double bandwidth against no return to zero. So there are a lot of parameters on which we can play to have the best design. That means that maybe tomorrow we are able to develop a modulation format such as I can put the amplifiers at 200 kilometers apart. For the time being, the figure I gave you are the current. Okay. Shall we stop here for coffee break and shall we reconvene at? Yes, 11. Restore the signal going through a digital, completely digital receiver. In this receiver, here you are at electrical level. You can process the signal with the 3R regeneration, and you can get again the signal as new, as it was here. The only change is that you have added one error rate bit out of 10 to the 12. Since your bit error rate is 10 to minus 12, you added one wrong bit every 10 to 1,000. But now you have, again, the restored signal, and you can go to another analog link. Well, I will insist a little bit on the analog behavior of links, because 30 years ago, we went all digital. With SDH, we went all digital. And we could have a single channel optical system working at some speed for 150. There is a lab record in the world, which means a system which has been built in a research lab, which is able to transmit 40 terabit per second over a few hundred kilometers on a single fiber. This is the reason. We can save both money and space. This is again, the reply to the question I got during the coffee break. The last bullet, a 3R regenerator, which is a regenerator able to receive, reshape, retype the pulse, is to be placed after the analog link. So you can go everywhere, but after a few hundred kilometers, you have to put an electrical receiver. This is the state of art, of course. What researchers are doing now is to get 3R regeneration directly at optical level, which means that sometime in the future, maybe 5 years or 10 years, we will be able to reshape the signal at optical level. The light pulse will be received and restored to the original shape. Second structure, the bus structure. In the bus structure, we have still a main path which is going through fibers and optical amplifier, but somewhere in the link, we insert an optical add-drop multiplexer. You saw yesterday or the day before yesterday OIDM, and what you know now is that from the total number of wavelengths which are passing through the device, some of them, which can be 0, can be all, or can be any number between, can be extracted, or in technical terms, dropped, and the same wavelength can be added. Of course, what we are doing is to change the signal over a given wavelength. Suppose we extract lambda 3. Lambda 3 is carrying an SDH signal which reached its destination. So we extract it. On the same lambda 3, we put another client signal, for example, a gigabit Ethernet. So we are extracting the signal and reusing the lambda to carry a different signal. Of course, to build an optical add and drop multiplex, it's a difficult task, and some part of the original lambda will pass through and will be added to the new lambda. This is interference, this is noise. So optical add and drop multiplex are a source of noise as well, just like optical amplifier. So we are easing our task of routing signals, because putting such kind of device along the network allows us some degrees of freedom to have the signal routed along the network, but we are also adding noise, so that even in this case, the maximum number that can be cascaded is limited by the total added noise. The picture is getting clearer and clearer. At the end, we will have a network in which source and destination can be selected by human intervention or by automatic intervention, but in the same time, we should be able to evaluate the loss of performance, which means the degradation on the signal, to avoid that the added noise is such that we cannot recover anymore the original signal with the wished bit error probability. Of course, as I told before, we can put a lot of optical add drop multiplex along the link and and in the network. Please note that if all the lambdas are extracted and all the lambdas are inserted, the optical add drop multiplex turns out to be a line terminal, a transmitter, or a receiver. I say this because normally vendors act just like this. They sell you an optical add drop multiplex and they tell you how to configure it to use it as a transmitter or receiver or both. Well, the add drop multiplex were shown in a linear bus, but in the reality, what is done is to have a complex network. This is a real network, the real backbone structure of Deutsche Telekom in Germany. And what is clear is that you can have optical add drop multiplex with more degrees, which means, for example, in this one, you have 1, 2, 3, 4, 5, 6 bidirectional links. Those are bidirectional links, so that instead of having only 4 degrees, if I have an optical add drop multiplex with one fiber going in, one fiber going out, the same for the other direction, I get 4 degrees of freedom. Here we have 12 degrees. In the total, we have 40 degrees of freedom, but it should be said that this is the Germany national backbone. So by means of a reduced number of optical add-drop multiplexer, I can cover a large country such as Germany. What's the meaning of this network? I have to go from Berlin to Leipzig. This is the shortest link, and at the beginning I will choose this link. But the fiber, the cable breaks. By adding the right, dropping and adding the right wavelengths, I can have a redirection of the signal so that by routing I can avoid the service to be interrupted. All this is done at the optical level. Point-to-point to multi-point links are another possibility. We shall deal with them in details tomorrow. In this kind of topology, there is one central office equipment whose name is optical line terminal, which sends signals along just one fiber. Somewhere during the path, the fiber is branched, is splitted in a number of different fibers, normally a power of 2, that is 4, 8, 16, and so on. And the signal which is sent from the central office is broadcast to any receiver. The name of the receiver is the ONU, which is Optical Network Unit, so that imagine that the optical line terminal is sending 2.5 gigabit per second signal. All the 2.5 gigabit per second signal, the signal will reach any of the optical network units. And inside each optical network units, the signal will be extracted for the part pertaining to that unit. On the other way, in the upstream direction, the situation will be a little bit different, but we shall deal with it tomorrow. So we had a view of topologies which can be used with WDM system or optical system in general. And we can start to make some sort of classification. The first one is a classification according to the use, according to the network application. So we have intra-office system for the 3 sub-areas of the network, which means metro access, metro core, and long haul. And moreover, we will have systems designed for use in submarine application. We can also classify the system according to the length of the maximum link they can transmit over. So we have intra-office, which means less than 25 kilometers, short haul, which is up to 40 kilometers, long haul, very long haul, and ultra long haul, which are 80, 20, 60 kilometers. All these systems are working in the third window, which means around 1550 nanometer. So, this is the situation. We have many possible applications. We have many type of links and many link lengths. We can use many fiber types. This was the question I promised to answer tomorrow. We can have many vendors sending nominal same systems. We can have many channels, 16, 40, 18. We can have many different wavelengths, because saying that we are using 8 channels does not imply that we are using those 8 wavelengths. We can use another set of wavelengths. So we are like the Babel Tower. How can we survive? Well, we could take a look of ITU recommendations for compatibility, which means we can, if we have systems for which the vendor says it is compliant with the ITU recommendation XXX, we know that that system can be connected with a system from a different vendor in the same class. Compatibility. What are we speaking about? This is another important matter. Compatibility where? We are generally speaking of an optical network, but we have not been very precise. An optical network is a general concept. In the real world, in the optical network, we put different systems from different vendors with different operating systems. And we have to decide what is compatibility and where we have to reach this compatibility. The most important concept is the concept of domain. In an optical network, we have several domains. A domain can be a country. A domain can be an operator inside the country. A domain can be part of the network of an operator using system from vendor A. So a domain in general is a set of equipment of the same class, of the same category, if you like. So now we have to specify at least 2 kinds of different interfaces. The interdomain interfaces, which are needed to connect different domains. Imagine you want to connect Rwanda network with the Uganda network. You are not sure they are going to use exactly the same systems that are used in Rwanda, so that this is an interdomain interconnection, because Rwanda and Uganda are different domains, different administrative domains. Well, somewhere in the ITU body of recommendations, there will be a specification saying that if you want to interconnect systems, you have to select systems with only 4 wavelengths. It's impossible to connect systems with 40 or 80 wavelengths. So please use only 4 or 2 or 1 or 8 wavelengths. Use these wavelengths. So wavelength from C40 to C43, where C40 or C43 are the ITU terminology for the frequencies, for the lambdas. And on each of these lambda, transport a signal equal to 2.5 gigabit per second. This is an intra-domain specification. But the same interdomain specification can be applied to a single operator or between operators. I don't know how many operators you have here in Rwanda, but if you want to connect domain from different operators, you have to use an interdomain specification. But even if you have a single domain, you can have interfaces between different apparatus, and this will be an intra-domain, which means internal to the domain specification. Moreover, normally we speak about longitudinal compatibility and transversal compatibility. The first part of the slide, the top part, is longitudinal compatibility. I have 2 different sites, site A and site B, and I want to connect them. I have equal fibers between the 2 sides, or I have just 1 fiber and I want to use different wavelengths. Well, longitudinal compatibility means that on the same link, I can install either the system from vendor A or the system from vendor B. So it means that the system I am buying is able to transmit 10 gigabit per second over 100 kilometers, provided that the attenuation of the fiber is such, the chromatic dispersion of the fiber is such, the polarization mode dispersion of the fiber is such, and so on. I have a set of parameters, but I am sure that going to buy systems with the given application code, we will insist in a moment on the meaning of application code, I will satisfy the requirements from any vendor I buy the system. This is longitudinal compatibility. Transversal compatibility, it's different. Before using ADSL, we used modems to establish a data connection. When you went to the shop to buy a modem, you simply said to the seller, please give me a modem V.90. You installed the modem at home, and you were sure that the modem would be able to interwork with the analogous V90 modem in the central office. Not the same vendor. You have been buying the modem that was available in the shop. You did not ask the operator, please tell me who is the vendor of your modems. This is transversal compatibility. Respecting a standard, V.90, you are sure that the 2 modems will interwork. The same is for optical fiber system or for transmission system in general. I have a link, which means, again, I have one fiber or more wavelength on a single fiber, and I can interconnect the vendor A system with the vendor B system, and it will work properly. So transversal compatibility means there are some rules, there are a set of parameters to be respected so that systems from different vendors can be interconnected. This, of course, is mandatory for interdomain application because, again, you in Rwanda have vendor A, in Uganda they have vendor B, and what you want is to connect the system. So the recommendation will tell you, use just 1 lambda or use 4 lambdas at this bit rate, with this power, with this color, and so on. This is the recommendation for compatibility. Is it everything clear, or I have to insist on something? The first one. No, this is an example, of course. The parameters are in the recommendation. Because you know that for using system conform with application code xxx.yyyy.www, etc., you can cover 40 kilometers of G652 fibers with such chromatic dispersion, with such power, and so on. This is only an example, a generic example, but in the reality, you will have your link parameters, and you can get them from the recommendation. It's like to buy a car. When you buy a car, you know from the instruction manual that your car is able to reach a speed of 150 kilometers per hour, that it will reach 100 kilometers per hour speed in 5 seconds, that the gasoline needed for 100 kilometers are 5 liters, and so on. If you compare 2 instruction manuals and you have the same parameters, the 2 cars are compatible. You can take out the figure from the instruction manual and you can put them in an ITU recommendation. So, car 1925 has this specification. Then you go to vendor A and you ask him, have you car 1925? Yes, sir. Vendor B. There, sir, have you car 1925? Yes, sir. So you can buy each one of them, either of them, and you are sure that the parameters will be respected. This is same slide than before, but in a more simple way, in which interdomain interfaces and intradomain interfaces are defined, but again there is another definition for interfaces between different vendors. Now we are ready to go for intra-office system. We are here, we are inside a central office, and this kind of system are characterized by the fact that they have no optical amplifiers along the link, because the distance, as you can see, is short enough to be reached by means of a direct link with no amplifier. They could be either single channel or multi-channel WDM systems. Well, here we have the general reference for such kind of system: a transmitter, a receiver, a main optical path. We will see in a few seconds what's the meaning of main optical path. And on this main optical path, just after the transmitter and just before the receiver, we have the two interfaces which are specified by ITU, which is the main optical path sending interface, S stays for sending or transmitting, and the MPI-R interface, where R stays for receiving interface. The compatibility is transversal compatibility, which means that the transmitter and the receiver can be of different vendors. The bit rate on single channel is either 10 gigabit per second or 40 gigabit per second, and distances are below 2 kilometers or below 25 kilometers. The two related recommendations are between brackets. Concerning the fiber, any fiber can be used for such kind of interconnection. Main optical path is composed not only by the fibers, but by any other component along the path, which means mainly connectors, splices, passive optical devices, for example, photonic cross-connect, which means switches. I can have switches to route the signal between two central offices. Connectors are needed because this is a flexibility point, just like SDH systems in central offices. You have a transmitter and you want to connect in a given direction. So you have a frame distribution, and you can simply put connectors on the frame. The same applies to optical system, of course. You have been told about the difference between black click approach and black box approach in the previous days. I will insist again on them because it's an important concept. Blank link approach, well, start from the black box approach. The black box approach simply means that the system is not known in details. The system is inside the box, a black box, and I don't know anything about the composition of the system. What I know is the characteristic parameters of the link, so that I simply specify two interfaces, one sending interfaces, one receiving interfaces on the link. I know everything of the link. I don't know anything, or I know nothing about the transmitter and the receiver. I know everything of the link. The reverse is the black link approach, in which I know everything of the equipment, which means transmitter and receiver, but my link is inside the box, so that I don't know what is inside. It can be just one fiber. It can be one fiber and 3 amplifiers. It can be one fiber, 2 amplifiers, and 4 optical add and drop multiplex. I don't know. But what I know is that there are 2 specific interfaces, and if my system is compliant with those interfaces, I am right. I can transmit. So, for intra-office system, we have a black box approach, so we define only the link. The link can include any kind of passive components. For application, for short, very short distance application, which is 2 kilometers, the fiber is of no concern, because we know that fibers are used by putting a reference value for the attenuation, which is equal to 0.4 dB per kilometers, for example, for the first class fiber. 2 kilometers is 0.8 dB, so we don't care. The attenuation comes from the other components, because maybe I have 4 connectors, 5 slices, I have two photonics cross connect, I have 1 add drop multiplex. So the maximum attenuation has to be evaluated, cannot be inferred by the length. Otherwise, it will be very, very low attenuation. The intra-office system are classified in terms of attenuation categories, which means this system will operate with an attenuation up to, or up to, or up to. So we have different values, and the system can be bought to be compliant with such attenuation class. The attenuation categories are on the 4th small bullet, and you can see that they are classified according to the maximum attenuation, which can be 4 dB or 6 dB or 12 or 16. Source and fiber, we can use laser operating in both windows on G652 fibers, or laser using third window on fibers G653 or G655. Fiber G653 is listed in this slide, in the following, and also in the ITU recommendation for historical reasons. But since they have been substituted by 655, and I think that it's very difficult to be able to buy one fiber G653, there is no need to consider them in the reality. The fiber G653 were very popular in the first 80s because they were the first fibers that you could buy and install, because we had no amplification, no amplifiers. The amplifiers were invented around 1994, so that the maximum we could expect was to send 4 channels or 8 channels WDM with low power, which means no linear effect. The only 2 countries to deploy such kind of fiber in a large scale were Italy and Japan. Italy built a network, a long-distance network in the 80s, which means from 1980 up to 1985 for about 4,000 kilometers of cables using 100% G653 fibers. Japan made almost the same thing. No other large installation could be found in other countries. So that now they are listed only for historical reasons. However, in Italy, for example, we are still using them, modifying a little bit the systems, changing the wavelength at which they work. Otherwise, it would be a huge investment lost forever. This is a table summarizing the parameters for intra-office system. Since we shall encounter a lot of such tables during the presentation, I will spend some time to clarify the meaning. On the top row, we have the classification according to the target distance. The target distance can be either 600 meters, of course, as a maximum, or 2 kilometers. The first target distance applies to systems in the same building. I am going, for example, from the 3rd floor to the 5th floor of a central office. Distances up to 2 kilometers are normally intended for inter-building links, which means I have a central office which is spread over to different buildings in the same environment, and I connect them with a short piece of fiber. Then we have the attenuation categories for 600 meters. We have only 2 attenuation categories. We miss the 16 dBs, but it is not needed since you are going very close to the starting point.